Okay, so because a variable name is a reference to an object, when you're dealing with lists, something you need to be very careful about is you do not want to modify a list as you are looping through that list, because you can easily trap yourself into an infinite loop without noticing. Here on slide 29, I have a list v4 initialized to contain 4, 9, 1, 16. And what I want to do is I want to modify this list so that it contains its original values followed by the square roots of those values. Notice that we're taking each one of the items in v4 and we're raising it to the 0.5 power, and we are appending that to the end of the list. Okay, so if I say for I in v4, all right, we're looping through v4. The first time through I is going to be a 4. The second time through I is going to be a 9. The third time it'll be a 1, and so on. And what I'm saying is v4.append the square root of I. My goal here is to end up with a list of 8 values. 2, 3, 1, and 4, the square roots of these original 4 values. However, what I actually have here is an infinite loop because I'm modifying v4 as I'm looping through v4, and so when the loop has made it past the 16, the loop discovers that, oh, now there's a 2 there, so it's going to compute the square root of 2. And then there's a 3, so it'll compute the square root of 3. And then there's a 1, so it'll compute the square root of 1. And it's going to keep building this list forever until I run out of memory, or Python itself decides to stop running this loop. So I'm going to hit Control-C. There we go. All right. So I now have this humongous list v4 with 180.5 million entries in it. What we need to do to avoid this is we want to loop on a shallow copy of the list, not on the list itself. And we can use the .copy method for this purpose. All right, so let me reset v4 to its original 4 values, 4, 9, 1, 16. All right, so now v4 is a reference to a list of just the original 4 values, 4, 9, 1, 16. And if I say for I in v4.copy, v4.copy will make a copy of that list as a separate object, and I can now successfully append into v4 itself the square roots of the values from the copy of v4. And this works fine. And now I have what I originally wanted. 4, 9, 1, 16 as the first 4 items, and then the square roots of these. Now, because I've taken an integer to a floating point power, these come out as floating point values, 2.0, 3.0, etc. Okay, so we've looked at lists, we've looked at the named member functions that you can use with lists. The next thing we're going to take a look at are what are called slices of sequences. And recall that a list is one example of a sequence. A range is also a sequence. A string is also a sequence. The idea is if we have some sequence object and we want to get some subpart of that sequence, we can use square bracket notation. Let me create this list V. V is 4, 3, 2, 9, 8, 7. I I just cannot seem to remember that last comma. Alrighty, so now we've got it. And if I give the name of a sequence object and a square bracket, I can now specify the initial item index that I want as a sequence, a subsequence from this, in this case, this list V, and a colon, and then the end value. Now, as with the range function, where if you were to say something like range 5, that gives you an iterable from 0 to 4, slices work the same way. So if I say sequence 0:5, that actually means from 0 up to 4. That is, up to 1 less than 5. All right, so if I say 1:4, that's going to give me a slice of V starting from index 1 up to but not including index 4. So I'll get index 1, 2, 3, but I will not get the value at index sub 4. So what I should get from this is a copy of that subsequence from within V. And since V is a list, this will also be a list. All right, so there we are. So I have a list 329. It turns out that if I don't specify an initial index for my slice, 0 is used by default. So if I were to say V of :3, this is equivalent to V of 0:3, and I'm going to get 0, 1, and 2. So I'll get the 4, 3, 2 part of that list, a copy of it. Similarly, if I don't have a value after the colon, then by default the length of the sequence is used. Now remember, the length of the sequence is an invalid index actually. In this case, the length of the sequence is 6, and if I were to ask for V sub 6, that would be an error. But when I'm talking about a slice, since we don't actually go up to the final index, it's fine. If I say V sub 4 colon, this is equivalent to V sub 4 colon 6, and what that actually means is 0, 1, 2, 3, 4, 5. Okay, so starting from sub 4, which is the 8, up to the sub 5, which is the 7, but not including sub 6, which would be an error. All right, and so there we have the 8, 7 slice of that list. Now I'm going to type in a different value for V here, and I won't make you watch this. Okay, so I've got my new value for the list V typed in. Remember that plus for lists is concatenation. So if I wanted to create a list that is a concatenation of a couple of slices of some list, that's easy to do. Here I'm saying V2 gets V sub 4 colon, that means V sub 4, which is the 13, up to and including the end. So that's going to give me a slice 13 minus 1, 0. And I'm going to concatenate V sub 1 colon 4, which means from 1 up to but not including 4. So that is going to give me the 2, 3, 7 part. And so what I should get is 13 minus 1, 0, followed by 2, 3, 7 as a list. And that is what I get. Now, it turns out that for any integer that you pick, regardless of what that integer is, and for any sequence, whether it's a list or a string or a tuple, the sequence up to but not including n concatenated with the sequence from n to the end is always going to be the same as the original sequence. All right, so here's V, and if I pick any value of n, if I say V sub colon 4 plus v sub 4 colon. That's going to give me back a copy of the original v. Now, bizarrely, these indexes don't even have to be valid indexes. If I say v sub 10, I get an error, of course. But when you create a slice using an index, even if the index is out of bounds, the slice will still make sense. So if I say v sub colon 10 plus v sub 10 colon, this looks like this should just be an error, but what it means is give me the slice of v up to but not including element sub 10. Well, there's only 7 elements in here, sub 0 up through sub 6. So I'm going to get the sub 0 up through sub 6 for this first part. And then v sub 10 colon says give me all of the items in the slice from 10 up through the end. Well, 10 up through the end is empty. So in effect, what this is the original v plus, that is concatenated with, an empty list. And so I get back the original list. All right, so v sub colon 10 is actually v, and v sub 10 colon is an empty list. And so what I've done is I've concatenated the original v with an empty list and gotten back a copy of my original list. All right, if you use a single integer subscript, that will give you a single item, as we know. So if I say, and here for some reason I'm changing v again. I'm not going to do this. This is silly. All right, so here's v, and if I say v sub 0, of course, that gives me the sub 0 item. If I say v sub minus 1, well, that gives me the last item, as I hope you recall. So that will be the 0 at the end. And if I say v sub 9, this is going to be an error. But as I've just demonstrated, whenever you ask for a slice, that is going to work even if one or both of the indexes that you give for the slice are out of range. All right, so here I have v, and if I say v colon from 0 up to but not including 1, well, that is a list of just one item. It starts from item sub 0 and goes up to but not including item sub 1, so I end up with a list of one item. If I say v sub minus 3 colon minus 1, now this may, at first when you glance at that, look incorrect, but recall that v sub minus 3 is the third item from the end, and v sub minus 1 is the last item at the end. But in a slice, we mean up to but not including that end index. So this is going to give me the items from sub minus 3 up to but not including sub minus 1. And this will give me the 13 and the minus 1. And as I showed, you can use an index that's crazy. If I say v sub colon 123, I get the original v. Now, if I say v sub colon, this is valid, and what it means is give me all the items from v, that is, give me a slice consisting of all the items from v from item sub 0 up to but not including item sub length of v, which in this case is 7. So from item 0 up to but not including item sub 7. That is yet another way of getting a copy of a list. Okay, a slice of a list is a copy of a portion of the list. And so if you say v sub colon, that means give me a copy of the entire list. Okay, and then here we have a couple of examples that or one example that I've already shown. If both of the indexes are out of range, you just get an empty list. In fact, even if the indexes are in a bogus order, if I ask for starting from 5 up to but not including 1, well, 5 up to but not including 1 doesn't even make sense, and yet I get an empty list from that. Okay, so as an alternative to making a copy by using the .copy method, I can use the subcolon slice notation as an alternate way of getting a copy. And you'll see code written in both of these ways depending on the knowledge level and stylistic preference of whoever is writing the code. So I've claimed that the .copy method and also the slice notation, I may actually not have remembered to say this about slices, but both the .copy method and slices are what are called shallow copies. And we need to be clear about what a shallow copy is. Now, even though it looks to us like we have values in this list, V1 here is 5. Let me put this together. V1 is gets 5, 3.14. It's possible, it's perfectly fine to have a list as an item within a list, just as you could have a string as an item within a list. So this list V1 contains 4 items, 5, 3.14, this list currently containing 987, and the value true. But actually what's stored in this list are references to these objects which are at certain locations in memory. Okay, so V1 does not directly contain 5. What it contains is a reference to where the 5 is in memory. Likewise, it does not directly contain 3.14. It contains a reference to where 3.14 is in memory. Similarly, it contains a reference to where this list is located in memory. That list itself does not actually contain 9, 8, and 7. It contains a reference to a 9, a reference to an 8, and a reference to a 7. All right, so this may all seem a little bit crazy here. But internally, that's what's actually going on in memory. Now, if I say V2 gets V1, since variables are references, V2 is simply an alternate reference to the same list that V1 is a reference to. And if I look at V2, I'll see that it certainly appears to be equal to V1. And if I use the is comparison, I see that V2 is V1. Now, let's take a look at what's going on here in memory. Okay, so what's going on in memory is I created a list and I set up V1 as the reference to that list. So V1 is a reference to a list of 4 items, but what that list actually contains is references to those 4 items. So we have a reference to 5, a reference to now this is a typo, obviously. This should be 3.14 rather than 2.7. And we have a reference to a list which in turn contains these 3 references to 9, 8, and 7. And finally a reference to true. When I then say V2 gets V1, that creates V2 as a reference to the same list that V1 is a reference to. Now, when I say here at the top of the first statement here in slide 38, I'm just redisplaying V1 so that we can see what it is. And of course, I still have my typo here, but we'll ignore that. When I say V3 gets V1.copy, this is making a shallow copy of V1. What we mean by a shallow copy is a copy of all those references. So when I say V3 gets V1.copy, what I'm getting is a copy of just these references. Okay, I'm not getting a copy of the 5, a copy of the, well, that should be 3.14. I'm just getting a copy of these references. So what that's going to look like is this. So when I say v3 gets v1.copy, that makes a copy of these references, and v3 now is a reference to that list of references. And all right, so the first item in v3 is a reference to the 5. The second item is a reference to the 3.14. The third item in v sub 3, that is the sub 2 item, is a reference to this list, which in turn is references to 987. Okay, so specifically, not only did I not get a copy of the 5, the 3.14, and the true, but I also did not get a copy of the 9, the 8, and the 7. I only got a copy of those references. Now, it is going to be the case that v3 sub 2 is the same object as v1 sub 2. All right, so v1 sub 2 is this reference, which is this list, and v3 sub 2 is this reference, which is referring to the same list. So if I switch back to my shell, and I ask whether, well, I'd better do my copy first, right? I'd better say v3 gets v1.copy. When I say v3, when I test whether v3 sub 2 is v1 sub 2, I get told, yes, that's true. Now, here's the dangerous thing. If I remove 5 from v1, now v1 no longer contains the 5. But v3 still does contain the 5. What's happening in memory is this. v1 has been modified. Its first item has been removed, and so v1 no longer has a reference to the 5. v1 now just has a reference to the 3.14 and to the list 987 and to the value true. But that did not modify v3 because v3 was a shallow copy of the original v1, so v3 still has its reference to 5. If I then append high to v3, well, that's going to add another reference to the end of this, now this list of 5 references, and that's going to be a reference to the string high. All right, so the upshot is I was able to remove an item from v1 and append an item to v3, and those modifications were independent of one another because of the shallow copy. But if I say v3 sub 2 sub 1 gets a -1, all right, v3 sub 2 is this reference, 2 sub 1 is this reference, and I'm changing that to a -1. Now what that means is that the reference to the 8 is replaced with a reference to a -1, and in memory, here's what's happening. Okay, the 8 no longer has a reference to it, and so it can be reclaimed from memory. Perhaps it does still have a reference to it somewhere. And I have modified this list to contain a reference to the value -1, which is stored someplace in memory. Now, because v1 still contains a reference to that list, I will see that change reflected in v1. The reason being that v3 was only a shallow copy of v1, not a so-called deep copy of v1. That is, v3 does not have its own separate list referring to a separate 987. It only has a reference to the same list that v1 still contains a reference to. So if I make that change, well, let me first add high to the end of V3. All right, so V1 no longer has the 5. V3 still has the 5 and also has high. But if I say V3 sub 2 sub 1 gets minus 1, not only has that changed V3, but it's also apparently changed V1. All right, I no longer have an 8 as the middle item in the sub 1 item of V1. I have a minus 1 instead of the 8. Okay, so both the dot copy method and the subcolon slice are shallow copies of the list, not deep copies making copies of all of the subcomponents of the list. Okay, let me get back to a list that does not have lists as subcomponents. Here's V. We know that we can change a particular item in V using an ordinary subscript. V sub 3, let's say, gets 123. And so what used to be 7 in the sub 3 slot is now 123. It turns out that we can also change an entire slice of a list to the values from some iterable. Let me reset V here to the simple example on slide 41. 0, 1, 2, 5, 4. Okay. If I look at V, I see that it has these 5 items in it. If I look at V sub 1 colon 3, that is a shallow copy of the items starting from sub 1 up to but not including item sub 3, pardon me. So that is the 1, 2 slice. But it turns out that on the left side of an assignment operation, rather than being a copy of that part of the list, the V sub 1 colon 3 actually acts as a reference to that slice. So if I say V sub 1 colon 3 gets some other list, I have now replaced the slice that used to contain 1, 2 with 9876. Okay, so my list has grown from 5 items to 7 items, and the slice that started out containing the values 1 and 2 has been replaced by the values 9876. If you want to get rid of a slice, you want to get rid of all of the values within a slice, you can say V sub slice gets an empty list. That has the effect of deleting all of those values in that slice. So V sub 1 up to but not including 5 would be the 9876 part. And I'm replacing all of that with an empty list. So now I just am back to the 3 elements, 0, 3, 4. A list is iterable. We've seen that we can step through the items in a list using a for loop, for example. But there are other iterables that we know about as well, like range or strings. If I say V sub length of V colon. Now, the length of V is an item that's beyond the end of the list. But if I use that in a slice, effectively what I'm doing is getting myself a reference to where the end of that list is. And if I say, all right, let's assign to that empty sublist at the end the values from the iterable range 5, what that does is to append the values from the iterable range 5 at the end of my list. I can use the same kind of trick to insert the values from some iterable into the middle of my list. So if I say V sub 1 colon 1 gets something, let's think about what v sub 1 colon 1 means. V sub 1 would be the 3. And what I'm saying is I want to replace everything in the slice from item sub 1 up to but not including item sub 1. Now, in effect, you can think of that as being like a pointer or a reference just ahead of that value in the sub 1 slot. And a string is an iterable. Recall that when I use a string as an iterable, it's going to be split up into 1 character wide substrings. The upshot is that I have now got these 3 1 character strings inserted ahead of the 3, what used to be the item sub 1. Okay, so that's pretty cool. That gives you a lot of flexibility about inserting and deleting subparts of lists anywhere that you can specify a slice. Okay, so we have very thoroughly covered lists, how to create them, how to access individual items or slices from them, also how to modify individual items or slices from them. We introduced 11 named methods that you can use to interact with lists. And we also described the important idea of shallow copies of a list. So if a list contains something like a list as a component, and you make a copy of the original list, the copy of the list will contain a reference to the same sublist. It will not contain an independent deep copy of that sublist for itself. Next, we're going to take a look at tuples. A tuple is enclosed in parenthesis characters rather than in square brackets as a list is. You do access individual items as you do in a list from 0 to n-1, or in reverse order from -1 to -n. Rather than using parentheses to access items, you use square brackets just like you do for a list. So this may be slightly puzzling to begin with. Anyway, here I'm going to create a tuple containing 7, 2, 3, 0. This tuple has 4 items in it. A tuple is a sequence. It is a collection. I can ask what the length of T is. And I can access individual items within T by using subscripts between 0 and 3, or subscripts between -1 and -4. Okay, so T sub -1 is the last item. T sub -4 is the first item within this tuple. And as we've seen, just like in a list, if you try to access outside the bounds of a tuple, T sub 5 is an error. Okay? One important difference between a tuple and a list is that you cannot modify items in a tuple. That is, a tuple is immutable, whereas a list is mutable. I still have this list V hanging around, and I can say things like V sub 5 gets 3.333, and that modifies an item from V. But if I try to say T sub 2 gets a 5, I get told a tuple does not support item assignment. Just as with a list, the items in a tuple can be of different data types. So it's fine for me to have a tuple containing an int and a str and a bool and a float and none. That's just fine. Concatenation and repetition with tuples use the plus symbol and the asterisk symbol, just as for concatenation and repetition in strings and lists. So here's T. If I say T plus some other tuple, 1, 2, 3, I get a new tuple, which is the concatenation of the tuple in T appended with 1, 2, 3. Or if I say T times 2, I get t repeated twice. And as we talked about with lists, and in fact in this case it's not really a special case because tuples use parentheses, I can go ahead and define a tuple across multiple lines because a tuple is already contained within parentheses, and parentheses allow me to continue my line. All right, so now I have a tuple T2 containing these 12 items. Now creating a one-item list is pretty straightforward. I can just say something like v, let me continue to have just plain v hanging around here. So let me create v1 as a list containing one item, 1. But creating a tuple with one item is a little more complicated. If I say t gets 12 in parentheses, actually 12 in parentheses is just an integer. Just like 3 plus 4 in parentheses is just an integer. So in order to force the parentheses to be treated as the tuple creating parentheses, we have to use this sort of funky notation of putting a comma after the one value that we want to have contained within our tuple. All right, so here, rather than being the value 12, because I've said t gets parentheses 12 comma, t is now a tuple containing the single value 12, the single item 12. An empty tuple is pretty easy. I can just use the parentheses for this. So t2 gets open close parentheses, does create an empty tuple. I can use the type function, by the way, to see that t is a tuple and t2 is a tuple. It turns out that if you use the commas between values, you don't even need to use the parentheses. Tuple packing basically allows you to leave out the parentheses. So if I say t gets 5 comma high, well, I made a typo, but that's okay. I hit enter by accident. So now I have a tuple with just 2 items in it. I can redefine t to refer to a different tuple by 5 comma high comma true comma 3.1415 comma none. That also defines a tuple, in this case a tuple of 5 items. So you'll often see tuples defined this way, just leaving the parentheses out. In fact, you can also unpack a tuple. More generally, you can unpack a sequence by having a tuple on the right side, or a sequence on the right side of the assignment operator, and an appropriate number of variable names on the left side. So t is 5 items long, so if I say A, B, C, D, E, separated with commas, gets t, the values within the tuple t will be unpacked, and each value, each item, will be stored sequentially, one by one, in these variables on the left. So A has a value of 5, B refers to high, C is true, D is 3.1415, and E finally is none. So of course I have to say print E in order to be able to see that. You can actually combine together tuple packing and sequence unpacking to accomplish what's called a multiple assignment. And this is very common in Python code. If I say A, comma B, comma C gets high 12, 2.7, the effect is that the 3 values on the right side of the assignment become the values referred to by the variables on the left side. So A is referring to high, B refers to 12, C refers to 2.7. Why in the world do we have tuples at all? Python is a relatively loose language in that it doesn't enforce very many rules. It's very rigid about indentation, but many other rules it's pretty relaxed about. Purely by convention, that is, this is a habit followed by skilled and experienced Python programmers, lists are usually assumed to contain values of the same type. Tuples are often assumed to contain values of different types. Of course, as we've seen, this rule is not enforced by Python itself. You can have a list of values of different types. You can have a tuple of items of the same type. But this is sort of by convention, that a list is thought of as being a collection of values that have the same type. A tuple is thought of as being a collection of values that have different types. A Python function, as we've talked about, returns one value, always exactly one value. If it does not have an explicit return statement, then a function returns the single value none. So, what do you do if you want a Python function to return multiple values? Well, a simple way of setting that up is to create a tuple of all of the different values that you want the function to return, and then you can return that tuple. Since a tuple is immutable, this is slightly safe for the calling code because the calling code is unlikely to accidentally change one of these return values that comes back with this returned tuple. So those are two reasons for having tuples. One is that we just want to have a conceptual separation between a collection that has all the same types and a collection that has different types. And we want to be able to return multiple values from a function, which we can do by cheating and putting those values in a tuple. A third reason for tuples, as we will talk about next week, are that sets and dictionaries store key values that are required to be immutable. And a tuple, therefore, can be a key for a set or a key for a dictionary, but a list, because it's mutable, cannot be. Okay, a tuple is iterable. I have this tuple containing these 5 items here. I won't retype this example on slide 54. I can say for I in t, do something with that value. I'm just going to print it out. All right, so this prints out 5 and then high and then true and so on. Because a tuple is iterable, if I have some list, I can insert the contents of the tuple somewhere in that list by using the list slice notation on the left side of an assignment. So here I'm saying v1:1 gets the contents of t. Okay, well, we already talked about the idea that 1:1 is a slice it's an empty slice that's basically like just ahead of item sub 1. And what I'm going to do here is to use my tuple t as the iterable that I'm going to insert into v ahead of the little h in this case. All right, so I've now extended v by inserting the 5 items read out of that tuple, that iterable t. Okay, a list is mutable. Both tuple and string are immutable. As we've said, if I have a list, I am allowed to directly modify the list. Let's be really careful about this. So here is my list, which has a certain ID number, and if I now say v plus gets some other list, well, let's use 3, 4, that's actually going to modify the list v. All right, v still has the same ID number, and it now has these additional couple of values, 2 and 4, appended on the end. If a tuple is immutable, what if we try to do the same kind of thing with a tuple? If we try to say t plus gets 3, 4, if a tuple is immutable, should this fail? Okay, that's strange. I didn't get any error message. Looks like the tuple t changed. Well, actually, no. Because what's going on here is that for a tuple, the plus gets operation is actually implemented by saying, let's start over again with our t containing 1, 2 initially. So t is a tuple containing the items 1 and 2. And if I ask for the ID of t, I get some number. Now, if I say t plus gets 3, 4, and then I look at the ID of t, what I'm going to see is that, no, I didn't actually change the original tuple. What I actually did was to create a new tuple. Because whereas for a list, the plus gets directly modifies the list on the left side of the assignment, for a tuple, the plus gets is literally implemented as t gets t plus, let me do 5, 6. And here now we can see what's actually going on. Because t here is going to give me a copy of the tuple that's currently referred to by t. I'm then going to append this tuple 5, 6 to that copy, and then the reference t is going to be changed to refer to that new tuple. Okay, so in each case, although it may have appeared at first glance that we were modifying the contents of the tuple, what in fact we were doing in the case of a tuple is creating a new one by using the original one and appending a copy of the original one with another tuple. Strings are also immutable. If I say s gets hello, I can't say s sub 0 gets h. All right, I get yelled at because assignment is not supported for a string. But I can, for the same tricky reasons that I could for the tuple, I can say s plus gets, comma, world, because this is not actually modifying the string hello. This is just modifying the reference s to refer to a new string, which is hello with comma space world appended. Okay, so what does that mean? Well, it means two things. Tuples and strings are not mutable, but it's easy to just create new tuples or new strings by appending using the original tuple or string. Okay, so let's suppose that we have this tuple here. Bald eagle I can't type. Soars. Well, I shouldn't create for myself such complicated examples. That would be easier. All right. Now, let's suppose that I want to change t to refer to a modified version of this tuple. Well, one way I can do that is to just take slices of the original tuple. All right, I can use slices with tuples the same way I can use slices with lists, or with strings for that matter. And so I'm going to say, give me everything up to but not including the sub 1 item, that is, everything up to but not including bald. Then let's have golden. And here, because this is needs to be a tuple in order for concatenation to work, I'd better remember my comma after golden. And then following that, we're going to append everything from item sub 2 to the end of the tuple. Colon, not semicolon. There we go. So now I have modified the reference t to refer to a new tuple that is based on parts of the original tuple t. So that's basically all there is to know about tuples. Since tuples are immutable, there's much less that you can do with them than you can do with lists. And yet tuples are nevertheless very widely used in Python programs.